Okay, welcome for part two of the characteristics of polynomial functions video. Um, you've gotten through this investigation, or at least you better have, otherwise this is spoiler alert central here. You don't want to continue with this video until you've tried some of the stuff yourself. That would take the point out of an investigation and discovery, which apparently educational research says that allows you to make more meaningful and powerful connections if you sort of learn things on yourself. So don't spoil it by reading the video without trying the investigation on your own. But it is important to make sure that you got out of it what you're supposed to get out of. So away we go. I'm going to reveal this sort of a little bit at a time. In general, we saw a polynomial function has this form, and it looks really, really confusing, right? Because we've got n's and subscripts and exponents and there's stuff all over the places. Someone asked, why don't we just use A, B, C, D, E, and so on? Well, usually we do. The only thing is in general, when we talk about a polynomial function, we don't know what the degree is in general. Like, how big is this n? For n equals 2, oh yeah, sure, fine. We can use ax squared plus bx plus c, and then we've got all the letters that we need. But if n happens to be 25 letters long, well, or 30 or 81 or 72, then we don't know how many letters to use. So we kind of use A1, A2, A3, and so on. So that's why this looks maybe more complicated than it needs to. We're used to stuff like this. This one is of degree 2, right? And it's a parabola. Next part. From the investigations, we saw this on the first the differences sheet the other day. The nth differences were constant. A turning point, remember, was it was a bump. It had, if a function was degree n, it had a maximum of n minus 1 bumps, turning points. Maximums or minimums would be the way to think of it. And what we were used to from grade 10 was a parabola. Well, a parabola had a maximum or a minimum. It's degree 2, but had 2 minus 1 turning point. We also saw that polynomial function degree n had at most n zeros. It could be the case that it has no zeros. Case of a parabola, if it has its turning point above the axis and opens up, well, then it might have 0, but the idea there is has at most a maximum, right? And we saw cases where it wasn't n minus 1 turning points. There were fewer than that, but this is our general conclusions. Okay, and the next part, the table, and I've got it filled out, so you might want to see this and then pause it, or you can probably copy as I'm talking. I'm going to try and go through really quick. First of all, notice that this table talks about the degree going up by 1, and then if I wanted to talk about what the equation of the polynomial function looks like in general, it's underneath there. Right, so y equals 5, where a is positive is just a line that's above the x-axis. A is positive, and then if a is negative, of course, it's down there. This is kind of a special case. We often don't talk about polynomial functions of degree 0, but we shouldn't be too upset or scared by ones that are. They generally fit our pattern anyway. But here's where we're used to talking of the linear functions degree 1. If a was positive, that means it had a positive slope. We would think of it in grade 9. It started low and ended high, right? A positive slope always has this sort of shape, and it might, it could go here, it could be there, it could be steeper or less steep or whatever, but it always started low and ended high. Even if I were to try and move it up, eventually it would start in the third quadrant and end in the fourth quadrant, or first quadrant rather. And similarly, if a was negative, we had a negative slope, it would start in the second quadrant and end in the fourth. No matter what, start high, end low. One way to think of this is if a is negative, it's just this one that's been flipped in the direction and flipped vertically over the x-axis. That's one way to think of it. And that's one way, once we get to the more complicated polynomial functions, that we could think. We could think of, if a is positive, well, that's just a regular uphill parabola, no worries. But if a is negative, it's a downhill parabola. You know, this is an uphill, downhill sort of deal. Smile and frown, you could think of it as. And notice here, the way I've written it, this has two zeros, one here and one here, but it doesn't have to. It could have 1 0, or it could have 0 zeros. Notice that wherever I move it, it still starts in the second quadrant and ends in the fourth quadrant. These are the sort of patterns we're supposed to pick up. Where if a is negative, it starts low and ends low. Starts in the third quadrant, ends in the fourth. Starts low and ends low. And then as the functions get higher in degree, they get more complicated. We saw cubic looked like this. In this general shape, I call them snake shapes, but hopefully you might call it an S shape or a squiggle or whatever you think of to remind you of the shape of a cubic graph, but it's degree 3 and it starts low and ends high. Similar to the line, right? Starts low, ends high, similar to the line. Now notice this one has 2 turning points, which makes sense because it's 1 less than 3. 2 turning points, 1 there and 1 there. And this one, the way it appears, has 3 zeros. 1, 2, 3. But notice if I change its position, it could have 2 zeros, or it could have 1 0. Is it possible for a cubic function to have no zeros? Well, no, right? It's going to cut somewhere, no matter where I move it. This one has 3 the way I've got it there. And notice, when a is negative, a being, we always let a be the leading coefficient. The leading coefficient is the number part on the highest degree term. When it's negative, it's opposite of this one. It starts high and ends low. It's like that one's been flipped, right? And starts high and ends low in a snake shape. When I get to a quartic function, a little more complicated, but quartic is degree 4, and it's similar in shape to the quadratic. Where a is positive, the leading coefficient is positive, it starts high and ends high. Or if a is negative, starts low and ends low. And by the way, I call these ones, the quartic functions, I call the cubic ones snakes, I call these ones m's and w's, right? When a is positive, it's a w. When a is negative, it's an m. So I call these m's and w's. M's and w's. That's the way I think of it. I'm not sure how you would think of it, but I think of them as m's and w's, the quartic functions. Okay, on we go. Here's a chart which basically breaks what we've got on the first one and thinks about, well, let's extend that to any odd degree. So any odd degree actually behaves a lot like that parent function, an odd degree basic function. If the leading coefficient was positive, a was positive, we saw that it started low and ended high, and that was the same for the other degree 3, started low, ended high if a was positive. So it started low and ends high. And that's true whether it's degree 1, degree 3, degree 5, degree 7. We saw that for all of those functions from the warm-up as well. They were all similar that way. They started low and ended high. Now, start low, end high is kind of not very technical math term. So let's starts is when x goes to negative infinity, what happens in behavior to y? Well, ending low is y going to negative infinity. High is y going to positive infinity. And now we can probably fill out the chart. Anytime it's an odd degree, it behaves kind of like a line. And when a is negative, it's been flipped, so it starts high and ends low. Starting high is y being positive infinity and ending low. And you're going to come up with your own sort of memory aids here, but I always think of for odd functions, it starts in one direction and ends in the other one. Low, high, low, where when it's even, it's the same. It's kind of like a parabola, and if it's a positive leading coefficient, if it starts high, it ends high. And if it's been flipped, it starts low and ends low. And this is true for any even degree power, whether it's x to the fourth, x to the sixth, and so on, right? It doesn't have to be these basic ones. It could be any degree 6 or degree 4. I could have all these extra terms on, and if this is the case, the leading coefficient is negative, it's going to start low and end low. All right, well, let's go back and fill in the details. Starting is x going to negative infinity, and starting high is y being to positive infinity, and so on. And hopefully this isn't too surprising for you. We're starting to get used to this terminology. And there's a couple of examples that are similar to the textbook stuff that asks us to kind of apply what we've just learned. I'm going to have a look and see how much time we've used up. I'm going to stop there, and we'll have the rest of these two examples in a third video from today.